Okay, so in this video, we're going to talk about, go over some exercises from the concepts on propositional consistency and proofs using logical rules we know. So one of the key things that you have to understand is that P implies Q has a lot of different meanings. So in other words, if you have a lot of English sentences, all of these things in English means P implies Q. For example, if you say P only if Q, that means if P is true, then Q must be true. When you say P implies a Q is a sufficient condition of Q is P, so if P is true, then Q is true. If you say Q whenever P is true, so that means P implies Q. This one says Q unless not P. That means if P is true, then Q is true. So the unless is sort of like a negation of that. So in other words, if you have P implies Q, you can just say, or P unless Q, you can just say not Q implies P. So my advice for you is to carefully think about these things. All right, so the next thing we're going to do is we're going to take a set of statements and convert them into a propositional system. So let's start with this statement. It says router can send packets. So we'll call that P. If it supports the new address space, so let's call that Q. So now let's translate that. So if we say P only if Q means that P implies Q. So the first statement says that we have P implies Q. So the second one says that router to support the new address space, which is really Q, it's necessary to have the latest software. So let's call that R. So in the next one, we say that P is necessary for Q means that Q implies P. So if you say Q is necessary for R, that means R implies Q. So we have R implies Q. So the third one says router can send packets to the edge system, which we call P, if the latest software system release is installed, which we call R. So if R, then P. So we have R implies P. So what we need to do now is to find a set of statements. R implies P, so we have R implies Q. So we'll take this one here. So we need to find whether there's a set of values for P, Q, and R such that this whole thing is true. So we know that for this to be true, all of these have to be true. If any one of them is false, then the whole thing is false. But we only need to find one set of things that makes it true. So we know that we're lucky in this case because if all are true, then P implies Q is true, this is true, and this is true, and therefore we found a set of things that satisfy that. So these statements are true, therefore this whole thing is true. So that's a good one, but you're not always that lucky. You might have to, one of them can become false, so the whole thing is false, but you may have to go keep looking for something here. So this all depends on what type of propositions you have. All right, so the next thing is to make sure that you understand these tables. If you have a proposition and true, the value of this whole thing depends on P, because if P is true, then the whole thing is true. P is false, whole thing is false. So instead of saying P and T, we can just replace it by P. Now, if you do double negation, obviously you get the same thing back. You can commute two propositions. If you have the same operator, in this case, disjunction, you can just remove the parentheses. If you have different operators, you will have to expand it. That's the distribution. The De Morgan law says that if you have conjunction, it becomes disjunction and vice versa, and so on. So let's keep that in mind as we try to prove these things. So let's start with this statement here. We want to show that P and Q implies P is a tautology. That's what we're trying to prove. Or let's say we don't know that, we'll see what we can come up with, right? So the first thing you want to recall is that P implies Q can always be replaced by not P or Q. So therefore what we need to do is we need to think about this as your not thing. So it'll be not P and Q or P. Now, by De Morgan's law, we can distribute this. So we have not P or not Q. Notice that the operator changed not to conjunction to disjunction or P. Now, because these are all the same operators, all these are the operators, it doesn't matter which order you write them, you can commute them. So if you commute them, you can see that this part here, not P and P, in fact gives you true. So we can just say this is the same as true or not Q. But is this a tautology? Yes, because it doesn't matter what the Q is, because this is a disjunction, because we have a truth here, the whole thing is true. So that's a way to prove that this is a tautology. Let's take a look at another one. Let's take a look at this one here. So let's see what we can come up with here. Again, we're going to think about this as the left-hand side, so we're going to negate that. P and Q, then O, this side here. But this side also, we're going to try to convert it to that. That's not P or Q. So now let's expand this. This is not P, O, not Q, O. So we have all disjunction now. So we can just remove the parentheses, it doesn't matter. So now if you combine things, you can see that not P gives you not P. And then we have not Q and Q gives you true. And we know that true or not P, doesn't matter what P is, this whole thing is true. So that's a tautology as well. You can try to prove these two, which I didn't prove. They're also tautologies, and you can follow the same argument to do that. So let's take another problem here. We want to show that this side here, is the same as that side. So we want to show that that is true. And so let's start with this side here. So let's start with here. You can say, I'm going to replace this by not P or Q, not P or Q, and then we have O, and we'll replace this by not P or R. So that's this one here. And let's try to simplify. Now we have O here, so we can just remove all the parentheses. It doesn't matter anymore. So let me get the eraser here, get some cleaning here. Let's just erase this one. Let's get the pen. Okay, so now we have not P or Q or not P or R. Okay, so I can take not P, combine them to get just a single not P, and then I will put the Q and R together. Now going backwards, we know this means P implies Q or R. We're done. So this is what we were trying to prove. So notice that in this case, I started from the left-hand side. I mainly apply this rule. P implies Q can be replaced by not P or Q. That's the big rule that you want to remember, so that you can remove all the implications and try to get something that's meaningful. So a proof is really something you start from the left-hand side here, and then you reach the right-hand side. So you prove that the left-hand side can be reduced to the right-hand side. So this is the end of the demo. If you have any questions, you can pose things to